mapping these ideas to probability. In order to do this, we need some kind of model that we can follow. And the model is the standard normal or Z distribution. This is a continuous distribution, and it's one of your most powerful tools. If we go back to that bell curve, which is the shape of this normal distribution, we can get a rough idea of how much of the area falls within a certain range using something called the empirical rule. Okay, this is also a rule of thumb. The technical name for this is it's a heuristic, and this gives us a rough idea. So remember, we have the mean, and notice that this one is stated in population terms. So the mean is mu, and the standard deviation is sigma. And we can ask, okay, well, if we start at the mean here in the middle and go up one standard deviation and down one standard deviation, about how much of the area under the curve falls in that area, plus or minus one standard deviation, which is in blue. And it turns out it's a little over 2/3, so it's 68% roughly, okay? If we go up another standard deviation, so plus 2 standard deviations, minus 2 standard deviations, which is now adding these red areas, so it's this whole area, the red and the blue and the red, that's about 95%. Now we're going to have a more precise number for that 95% eventually, but for now, roughly plus or minus 2. And if we go up another one, plus 3, minus 3, okay, so now we're 3 standard deviations out on both ends. That gives us almost everything, 99.7%. Okay, so that's a rough way of thinking of this, and it gives you the sense that really almost everything falls within plus or minus 3 standard deviations. So if something is further away than 3 standard deviations, it's probably unusual. Okay, because if we expect 99.7% of things to fall within 3, that means 0.3% are going to be outside of that, which is not 0.03, it's 0.0003. So, okay, that's a good rough sketch, but we're going to need even more precision than that. So we're going to define the probability f of x as being non-zero. Okay, so it's greater than 0 for all the x's in this distribution, and the total area under this curve must add to 1. Okay, so once we have the probability, for example, on one end, then the complement of that is the probability from there to the other end. Okay, so they are complements. And we're going to define the function f of x as the probability that x is less than or equal to some number. So notice here that we put the equal sign here. So we're including everything up to and including a point. Because this is a density function, we don't actually talk about the probability of a specific number. So we have to put the equals somewhere. And so we put it in the accumulation up to that point. So we accumulate from the left to the right. Okay, so the accumulation goes this way. So we have 0%. Eventually we have 5%. Get to the middle, we have 50%. Blah, blah, we have 95%. And eventually we have 100%. Now, where do we have 100%? At positive infinity. And where do we have 0? At negative infinity. But we're just not going to worry about that too much. Okay, here's the precise formula for this curve. Remember, we said we can approximate it with sort of straight line things like triangles and stuff, but it is a curvilinear function. And so you can see that pi comes in here, which is, often in math when we've got something with a curve, we've got a pi in it. We also have, notice, sigma, our standard deviation. We've got it here too. That's actually the variance. We've got the mean, mu, and this is the value that we're looking at. E, right, which is like the exponent function, is the inverse of the natural log. So e to the 1 is equal to 2.717 approximately. And if you take the natural log of e, you'll get 1. Can we simplify that? Because that's pretty horrible looking. And indeed we can. So there's something called the standard normal curve. And for that, the mean is 0 by definition, and the standard deviation is 1. So it's centered at 0. And then we go up 1 and down 1, up 2 and down 2, up 3 and down 3, right? And every standard deviation is a 1. So if we look at that function again, what that does is it means our sigma, this, is 1, this is 0, this is 1, okay? And that simplifies things a lot. And then this thing, the basically x minus mu negative, becomes a z-score. Okay, so we will work with this simplified function as the standard normal function. If we can take our data and map it onto this model, that will help us figure out the probability of finding different values and points in our own data. We don't want to calculate this every time we want to use the normal curve. No, 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 not fun. So we're going to have some help, but luckily we have, goodbye, we have help. We have a standard normal curve or Z table, and we also can do this in R. So we have R and tables to help us. So here, for example, is the negative Z table, and this is in the back of your textbook. I will also give you one for reference, although we'll learn how to do this in R too. But for the sake of understanding, notice the picture shows you accumulating area from down here in the negative infinity up to a point, okay? And the negative z's only go to the midpoint. So you can see down here is 0.0. And the area associated with that is 0.5. So the area in the left-hand half of the curve is 0.5 because it's half. The z-scores are these digits. These are the first 2 digits of the z-score. And then these are the second decimal place, okay? And what you have in the body of the table, all of these numbers, are areas or probabilities up to and to the left of that number. So let's look at negative 2.81, okay? And let's look at it a little bit more close up on the next page because it's hard to see. Okay, this is blown up a little bit. So negative 2.81. So negative 2.8, and then the second decimal place is 1. So we're going to be in this column, and we're going to be negative 2.8, and we're going to go over to that column, and we have 0.0025. So the probability that x is less than or equal to negative 2.81 is equal to 0.0025. In other words, not very likely, and that makes sense because we just saw that like most things fall between plus and minus 3. And while this is close to -3, it's definitely getting out there. Okay. So to do this in R, you use what's called the p-norm function, and then you just put in your z-score. So if we put in p-norm -2.81, we will get the same thing. What about a positive 2.81? Okay, we can say what's the area to the left of that? We can look at it in the table, or we can just put a positive 2.81 into our p-norm function. And if you think about this for a second, that's pretty far out on the right, so it's probably a big number. If we look at it in the table, this is the positive z's. We need for, let's see, z is positive 2.81. Again, the second decimal is 0.01, so that puts us in this column. And we're going to be in the 2.8 line. So we come over here and we get 0.9975. So the probability of it being less than or equal to 2.81 is 0.9975. Okay. So that's what the table gives you, and that's what p-norm gets you. But what about if we wanted the area to the right of the z-score? If you're doing it in the table, then you would take 1 minus. So the table, you would take 1 minus the probability. Okay. And so for the last one, we had 0.9975. So we would take 1 minus 0.9975. And wow, we get 0.0025. Huh. That makes sense because that's actually, which is equal to the probability of it being less than or equal to -2.81. Right? It has to be the same because the table's symmetric. So whatever's in the left tail is in the right tail beyond the positive value of that number. To do it in R, you need to add something to your command. You add lower tail equals false, put it in caps. So if we put in p-norm -2.81 lower tail equals false, we will get, now remember this is the negative that we're looking at, so we will get 0.9975. Okay, and if you do that to get the area to the right of 2.81, you'll get 0.0025. You can also, if you prefer, do 1 minus p-norm of the z value, and that will also give you, that's basically doing in R what we just did up here by hand. Like here we did 1 minus that. You can also do it in R that way. So you have a couple options on how you want to do that. So to sum up, the area to the left of z equal -2.81 is 0.0025, which is also the area to the right of positive 2.81. The area to the left of positive 2.81 is 9975, which is also the area, to the right of -2.81. And so these two are complements. These two are complements, right? And so their areas, their probabilities have to add up to 1.